Hello and welcome to the first part of the e-learning module for Session 5 of Operations Analysis, where we will deal with transportation and assignment models. We still had on our agenda to look at the sensitivity analysis and the link between the primal problem and the dual problem. So this is what we are going to do in this video, and then we will look at the special structured linear programs, where we look at transportation and assignment problems. And then we will have questions and outlook to the next session that we will deal with over the discussion board on Blackboard. So first of all, let us consider a linear program. Once again, we have here a mathematical model given for profit maximization. So we have given some decision variable here and some coefficient that gives us the profit of the problem, and then we have some constraints that gives us the limitations of our problem. It's also called a resource allocation problem, where we have here given the production rate of, for instance, a resource, and the decision variable of our problem. And then we have some resources allocated to the activities given by the BI, that is also our what we call right-hand side in our linear problems, when, for instance, dealing with the simplex, and here it's giving the capacity of the activity. So now, as we deal with resource allocation problems, a good question of management is how to decide which resources to allocate to which activity. So which capacity we want to make available for some kind of activity that can be the production of a new problem. So the decision of the management is to deal with the question of how much resources should be allocated to one activity instead of another, which could, for instance, be the production of a new product, but it could also be dealing with the budget of a project you are dealing with. And then it's nice to have a decision support that gives you arguments for the management to say why your budget should increase despite of the budget of a colleague of you. And the simplex algorithm gives us an answer to this problem by looking at the dual version of our original or primal problem. So we can look at the shadow prices of that. Let's take a simple example that we have dealt with already when we were doing the simplex algorithm, and let's have a look at the shadow prices and also the sensitivity analysis, and also to the dual version of the problem. For that purpose, we go to Excel, and here I have already stated the mathematical problem to you. So here we have given the coefficients of the objective function for x1 and x2. And here we have the constraints of the problem given by our three constraints, and the right-hand side that limits the capacity that can be allocated to the production of these products. Here in green, I denoted for giving this problem to the solver the used resources, or the utilization of the resources, given by the multiplication of the coefficients multiplied by the decision variables that need to be given to us by the solver then in Excel. Of course, we can do it also by hand, but here we use Excel for that purpose. So here is the objective function. We want to maximize the profits given by the coefficients of the objective function and the decision variables. So this problem you recall that we give to the solver. So we define here where we find the objective of our problem. We want to maximize it, so we click on maximization, and then we give Excel also the changing variables that here we have given in yellow. And then the next thing we need to give to Excel is the constraints, so the boundaries, and for that purpose we give the used resources to Excel and say this should be smaller or equal to the right hand side. Yeah, and then we are done. So now we want to define our decision variables non-negative, and we want to use the simplex algorithm to solve this problem. When we are done with that, we see that this is actually the optimal solution that we have found also by applying the simplex algorithm in the tabloid form by hand. And here now we have several different reports that we can invoke. One is to get the answer of the solution, and another one is to get the sensitivity and the limitations of the problem in a different report. I'm not gonna click on these reports because I have already done it. And if we look now to the sensitivity report here, then we can get some information about the shadow prices of the resources. So what are these values now telling us when we look at the shadow prices for the resources? We have given a 0 for the constraint, for the first constraint, where the shadow price is 0. For the second one we have 1.667, and for the third one we have 5. But what are these values now telling us? So the shadow prices of our resources now give us the marginal increase of the objective function when we increase this resource by slightly 1 unit or 1 amount of this resource. So now if we would increase the resource 1, for instance, as we have seen, that is given here by the red line. If we would increase that resource by some marginal unit, so we push it a little bit outward here, then the gain in the objective value would be 0. But we have seen that if we do increase the other two constraints, or the capacities of these constraints, by 1 unit, then in fact we gain something. So for instance, if we increase our third constraint, that is given here by the green line, then we would gain a value of 5. And if we look at the second constraint given now by the blue line, we see that here if we increase by, for instance, 10 units the resource of that resource, then we can gain a value of 5 divided by 3, and this is the shadow price that we have just seen by 1.66 and 7. So increasing our resources by 1 unit gives us then the information of how much we can gain in the objective function by doing so. This can be also stated as follows, where we have the optimal value for zeta, which is equal to the dual variables multiplied by the capacity. Our example, we have seen that if we increase B1, then we don't have any gain. If we increase B2, then we have a gain of 5 divided 3. And if we increase 1 unit in B3, then we have an increase in 5. And these scheduled prices are the dual variables that we can find out when looking at the dual problem of our primal problem. And we recall that we had to flip the problem so that we get the dual version of it, meaning that now we are looking at before we were looking at a maximization problem, now we are looking at a minimization problem, and that for the constraints now we have larger or equal to, despite what we had before, which was smaller or equal to. So let's look at the solver. Here, just shortly, we defined the problem with the objective function value that in this time we minimize. We have given the changing cell variables in yellow. And now you see in the constraint that we have the changing or the utilization of the resource. And now we require this in green to be larger or equal to the limitation, or to the right-hand side that we have given in the problem now. The rest remains equal, and if we say solve, then once again we have the reports that we can look at. And here we see now the values that we just saw in the shadow prices for the sensitivity report on the primal problem. Recall here that these are the same. So when considering now a sensitivity analysis, the question that we want to answer is how much can we have made errors in estimating our parameters to our model that would not change the optimal solution? Or in other words, which are those parameters that we need to take special care of, because if they would be erroneous, they would change the optimal solution. The question is, why would we really be interested in this? And this is because, well, the sensitive parameters need to be taken special care of, because these are the risky ones. If we make an error in these, then our optimal solution will change. So the question is, how can we identify now the parameters that are sensitive to our model? Normally, we consider only the resource parameters, so the right-hand side of our problem given by BI, and the parameters that denote our performance gain given by CJ. The other parameters given by AEY that give us the production rate, for instance, or the applied technology, they normally, we would consider them as being quite robust, so we would not question them too much. The question is now, when we go through now these parameters and we start with the performance parameters, how much can these vary until our optimal solution would change? Or in other words, how much can we vary them and still have the optimal solution that we have calculated? This can be answered by looking at the graphical solution once again, and we can also calculate it, what I have prepared here. So if we vary now, so now the allowable range for the coefficient C1 can be calculated by taking the ratio of our coefficients of the objective function. And then we require that the other one, so C2, remains constant. It was given by 20 in the objective function. And then by simply doing some algebra, we can calculate the allowable range that is between 13.3 and 0. And in fact, we can vary the inclination of our objective function until the point where it would intersect here with or have the same inclination as our constraint 2. And we can also, on the other hand, decrease the coefficient C1 to let it be 0. Then we have the intersection with the third constraint. And this is then where we would have the same inclination as our third constraint. The same is valid now for C2. Here we take it in 2 steps because we have the coefficient in the denominator. So first we use some algebra once again to calculate the allowable decrease of our coefficient that is given here by 15. So we can decrease our coefficient C2 to the value of 15. And if we do so, then we would in fact have the same inclination once again as our inequality 2. And if and that is now tricky here. If we want to know how much we can increase this value, then type it in our program for the graphical solution that we can increase C2 to infinite because that would just make it have an inclination of 0. And the last question is now how much can we vary the capacities of our resources and when would the basic solution, the basic feasible solution change. And this is given by the final value in Excel, for instance, in the Excel report. So once again, if we look at the table, we see here for constraint 1, for instance, that the capacity was given by 100 and the allowable increase is now infinite, while the allowable decrease is 10, meaning that we can have an allowable range in between 90 and infinite that this resource can vary. And if we look at the graphic, in fact, when we change now the values for the first constraint and we say minus 10, then we see here that this constraint won't now come close to or be in the point of the optimal solution. So here now we would have a new intersection point for the optimal solution. Now a value that is higher. We see that this constraint is now repositioned to the outer space, meaning that here it does not pertain to the optimal solution, and that means that we can increase this capacity as much as we like. It would not change anything to the basic feasible solution. If we do the same now, just another test for the second resource, here the value was 720, and we are allowed to increase it by 60 or decrease it by 180. So if, once again, we look at this resource, then we can make this visible in just seeing how much this can change. So we said we can decrease it by 180 And in fact, we see in the graphic that at this point here, it would hit our constraint 3. So the basic feasible solution would change. And the increase was by 60. So if we increase it by 60, then there would be a new intersection point with the first constraint. Yeah, and if you have questions to this, then I'm happy to answer them in the discussion forum in Blackboard. Thanks a lot for listening.